This one has this graph. All right, so I did not spend a whole lot of time, or at all, talking about these kind of potential energy curves. Does that bother you, Jake?
What?
Does that bother you?
No.
Because I mean, my understanding from checking your reading score is you're a successful reader.
Yeah.
Excellent. Just checking. It is a compliment. It's also a recognition that some things I don't want to have to go over because they're just not that big a deal. And I feel as though, although it's highly likely this kind of stuff will be on the exam.
Who needs it?
Well, you probably don't, but other people may. Now, this is, I think, positioned on the bottom here. These kinds of graphs, they show up on the exam from time to time. They have been full FRQs before as well. When they are full FRQ, in general, what they are looking for you to do is to be able to interpret the energy of the graph. I'm having a difficult time drawing this the way it looks over here, but I'll continue to try and do my best. I know that at 5, it's here. At 2, it is here. And at B, it is there. And it's some kind of continuous curve like that. So what you should be looking for is twofold. They will sometimes have a line on the graph somewhere indicating what the total energy is of the system. Something like this. They'll say this red line might represent the total energy, but this is a potential energy curve. They are, if they do this on a problem, they are trying to tell you that this part of the graph from here to here represents the potential energy, while this part from here to here represents the kinetic energy, and that the total energy here is a constant. So these graphs generally are going to be about interpreting not necessarily how much the potential energy is, but what the relationship is between the potential and the kinetic. They will sometimes, and I know you guys don't see what I'm doing here, but this is actually the notes. I sometimes want a good example for you guys who have worked one before I actually go through something. They will sometimes, have this line someplace like this. If they do, what they're telling you is that the object is trapped. It can't pass this point. It doesn't have enough energy to make it to here. If that red line represents the total energy of the object, and this is the potential energy curve, then this object can only be found here because it doesn't have enough energy to be on the other side. So these problems are not uncommon, and they're looking for you to interpret what it means to have a specific or finite amount of energy based on the graph. Now, this problem isn't exactly like that. This problem is pretty straightforward. It says a particle has a mass of 100 grams. What minimum speed does the particle need at point A to reach point B? They are telling you that the object must have an energy that is sufficient for it to make it here, to this location. So they want to know how much kinetic energy it would have to have. Well, it seems to me that it needs to have a total of 5 joules of energy. And it has 2 joules of energy at A. So in order for it to make it there, it must have 3 joules of kinetic energy. Now they're looking for the speed, so 1/2 mv squared has to equal 3. The mass was 100 grams, so that's 0.1. Now, part B says, what minimum speed does a particle need at B to reach point A? What minimum speed does a particle need at B to reach point A? Well, we're going to redo this, I guess, and yes?
Could you go over how you got 3 again?
The difference from here to here is 3 joules.
Oh, okay.
That okay?
Yeah.
So for the second part, they want you to be able to go from here to here. It's going to take 5 joules of energy because we have no potential energy at point B. So it's the same problem again. Just this time, 5 joules is required to get there. That's it. Any follow-up on that? You guys can find V. We're not going to do algebra. All right. Ava?
Number 7, letter B. 7 The one that's about converting potential to electrical energy.
Okay.
I did A.
Suppose dam is 80% efficient. The word efficiency might have a confused meaning here. I'll wait patiently for you guys. I'm in no hurry. Your test is tomorrow either way. We good? Ready? The word efficiency here is a ratio of how much energy you get out based on how much you put in. And it could also be written as power out compared to the power in. But it's just a ratio. So if they say it's 80% efficient, then that means that for every 1 joule of energy you put into it, you only get maybe 0.8 joules of useful energy out. Generally, all machines have an efficiency rating. Nothing is 100% efficient. You might be able to get 100% conversion of energy, but nothing is 100% efficient. And it's a delicate point, and it's not one that's necessarily one you need to focus on. So if we had an opportunity to talk about thermodynamics, we could get into it a little bit, but we don't. So in this case, it says the dam is 80% efficient at converting the water's potential energy to electrical energy. How many kilograms of water must pass through the turbines each second to generate 45 megawatts? So 45 times 10 to the 6th watts is what we're talking about, which means that the dam has to convert 45 times 10 to the 6th joules per second. Now, we talked a little bit about the height difference of the water. I think that might not have been in this class, but it indicates that water is flowing over a spillway that's 33 meters tall. And if we looked at 1 kilogram of water as it falls from the top to the bottom, the amount of potential energy that water has when it's at the top of the spillway is going to be 1 times 10 times 33, MGH. Now you'd have to use 9.8 if you're going to use turn this in for mastering. But that looks like 330 joules per kilogram of water. Because hear what I'm saying. I'm trying to be very clear about this. You get 330 joules per kilogram of water, but the dam is only 80% efficient. So the electrical energy you get from this is only 0.8 times 330 joules per kilogram from the fall of the water. This represents how much electrical energy you get per kilogram of water. Everybody understand what that is? And we need 45 times 10 to the 6 joules per second. And I'm only going to get whatever that is. Can somebody multiply that out for me so I can point at it and talk about it? All right, so the amount of energy per kilogram is 264 joules per kilogram. Now, if I divide these two numbers, I will get the kilograms per second that has to flow through the dam. This is the joules per second that I need, and this is the joules per kilogram that I get. So if I take 45 times 10 to the sixth joules per second, which is required, and divide by 264 joules per kilogram, this answer will be in kilograms per second. That represents the amount of water that has to flow out of the spillway. There's no formula I'm working from here. I'm just looking at the units. If you want a formula for this, then what I would encourage you to look at is power equals energy over time. In 1 second, the dam needs 45 times 10 to the sixth joules of energy. It needs that every second. And you only get 264 joules for every kilogram of water. If you divide those, that tells you how many kilograms of water you need to produce the required energy. That is per second. I will not have one like this on the test. I'm not saying I won't have power on the test, but I won't have something like this on the test. It's number 22. This new spring has a spring relationship minus kx cubed. I'm sorry, they want me to use Q. All right. Just so you guys know, this has been on the exam. This will be on the exam. These kinds of problems are on the exam. Question A, what is the units? I don't care about that. You should know it's newtons per meters cubed. B, find an expression for the potential energy of a stretched or compressed spring like this. All right, so this is probably where I would pay attention. And there's every reason to believe I could put this on tomorrow's test. I have no trouble with this kind of question. I want you to be aware that it's been on the exam before. So if I just wanted to pull an exam question, this is out there. So by definition, work equals the integral of f dot dx. So in the case of this unique spring, that's minus qx cubed dx. And let's just provide a little bit of reference for it. The negative sign here is to indicate already that the force is in the opposite direction of the displacement. So if I displace the spring this way, the force from the spring will be that way. So it's already handling the idea of the cosine, so I don't have to worry about putting the cosine here. That might not make sense to you guys, but I'll say it again. This relationship, having the negative sign already in it, is already doing the cosine part for you. So I'm not going to redo it. And I think that you might not recognize this, but the work by the end of this should be negative. Work done by a conservative force like this should be negative. Remember the whole box thing. I would want a box that has kinetic energy to be brought to rest with the mathematics. Either way, this part of the problem isn't all that big a deal. We're going to start with the spring not stretched or compressed. And we're going to compress it to some position x. So to find out the amount of work done on the spring, I'll do a little bit of calculus here. First, I'll bring that negative q out front. And I'm going to integrate from 0 to x cubed dx. My recollection here is that this is a standard polynomial. So I'm going to add 1 to the exponent and divide by the new exponent, which will give me 1/4 x to the 4th evaluated from 0 to x. This will be the work done. So work's going to equal negative 1/4 qx to the fourth minus 0, but I'm okay with leaving that out. This is the amount of work done in compressing the spring. They did indicate that I was allowed to say that the original position of the spring was 0, but they might want this as x minus xc to the fourth. They might, but they should accept this as the answer because they told us xc was 0. Yep.
The answer's not negative on my screen, because I put it in as negative and then it said it was wrong.
All right, the reason is because I found the work done, but I'm reading the question more closely, and it says find an expression for the potential energy. And the potential energy would have to be minus the work done, so that's why. Potential energy is minus the work done. That's why they're just, by saying potential energy, they are asking you to change the sign to positive. Potential energies will be positive, folks, unless we're talking about gravity. All right. A sprung-loaded toy gun shoots a 17-gram plastic ball. What is the launch speed if the Sprung constant is 4.2 times 10 to the fourth newtons per meter cubed, and the Sprung is compressed 15 centimeters? This is a conservation of energy question, or at least I believe conservation of energy would be the best way to go. So, two states of the question. I see the state where the Sprung is compressed and a ball is placed here. And then I see the state where the Sprung has been released. And the ball is exiting the Sprung. And we're asked to find its velocity. So I don't think this is too big a deal. There's spring energy here, but no kinetic. And there's kinetic energy here, but no potential. And since this can be considered a conservative force, or the only thing doing work on the system, these two things have to be equal to each other. So 1/4 qx to the fourth has to equal 1/2 mv squared. Is that far enough, or should I continue? That's good? All right. A 40-gram ice cube can slide without friction up and down a 30-degree slope. The ice cube is pressed against a spring at the bottom of the slope, compressing the spring 10 centimeters. The spring constant is 20 newtons per meter. When the ice cube is released, what total distance will it travel up the slope before reversing direction? All right. Let me just state clearly the book is not clear where the spring is. And by not being clear, and I found this problem with both this book and the other Pearson book, there's potentially two answers here, and this is just sloppy test writing or problem writing. One of these is much easier to do than the other. So if you take my meaning, which one of these is going to be a more difficult problem to do? The one on the left or the one on the right? The one on the left. Yeah. These are not the same problem. And if you don't understand why, then you weren't paying attention the other day. The one on the left, when I compress the spring 15 centimeters, I reset 0 for potential energy to be at a new lowest point. I'm basically, is it 15 centimeters? 10 centimeters, sorry, 10 centimeters. I'm resetting where 0 is. I'm saying the lowest point is now where the spring is compressed. But if I pull the spring back, oops. If I pull the spring back on this one 10 centimeters, I don't change the potential energy of the block. They are not clear in the question which of these is the case. Now, I just want you to know, this is like AP 1 level work. This is AP C level work. I mean, the question on the left has been on the exam. More importantly, as I'm choosing problems for tomorrow, I could pick the one on the left. But their answer that I'm looking at right here is the one on the right. And there's a difference here. Yeah.
I tried doing it the way on the left, so when you do it, can you do it the way on the left?
Yeah, that's fine.
Well, I will do it whatever way you guys ask. But what I'm trying to say is I know that I assign problems from mastering because it's convenient. And because I want you guys to become accustomed to using an online submission form for your homework. But they're not clear here. And unless they provided a diagram, it could be either of these, right?
Yeah.
But one of these, I think they believe both of these are the same. I believe that they hired some is super easy. When I compress the spring, it's gravitational potential energy. The box slides up to here, and I'm sorry, I said the wrong thing. On the bottom is elastic potential energy. The box slides up to its highest point, and it's gravitational potential energy. That's pretty easy. And I only have to worry about this height. On the left, it's going to be a little more difficult because when I pull the box back, it's all spring energy. But the height that the box goes is going to have to include that 10 centimeters. It's not a big deal, but it's a deal, especially because it's at an angle here. Now, if I was to do this problem all in terms of conservation of energy, I would not be answering the question how far along the ramp it goes. Because conservation of energy won't tell me how far along the ramp. Conservation of energy is going to tell me how high on the ramp it travels to. So if they want how far along the ramp it goes, that's answering a different question. It has to do with this triangle though, so it's not that big a deal, but I do have to consider that the triangle part of this problem might be separate from the conservation of energy part of this problem. And if you don't understand what I'm discussing, please ask now. Okay, when we did this in class, we talked about the work done. I'm going to do this from conservation of energy. Up here will be the height it makes it to. That's going to be based on gravitational potential energy. That will be mgh. Down here, the total amount of energy will be elastic potential energy. That will be 1/2 kx squared. Now, I will come back to how x and h are related. Let's just go ahead and figure out what h has to be. So I'm going to slide this up a little bit. Maybe. Stupid program. You know, there's no other program like this, but this one makes me crazy. Where was I? There? Good enough?
Yeah.
All right, so they tell me the spring constant is, let's see. They don't tell me the spring constant. Do they? 40 gram cube. Oh, 20 newtons per meter. There we go. So 1/2 k x squared equals mgh. So h will be kx squared over 2mg. That will be 20 times 0.1 squared over 2 times 0.04 times 9.8. Your mileage may vary if you guys had different numbers. Can you guys bust that through? We're gonna need this number to figure out the answer. Yes, sir?
Did you change the whites
Sorry. And Jackson has told me that the red is impossible to see back there. I apologize. That better?
I got .255.
I'm okay with that. I don't know what it is, so I'll say 0.255. You second it?
Yeah.
All right, can I keep going? 0.255? All right, so I'm gonna flip to another page. And just, it was 30 degrees, but the block is now up here. And it is 0.255. We were supposed to figure out how long along the ramp it went. Now, I'm thinking all we should have to do is assume that the 10 centimeters was based along the ramp. We pulled it back 10 centimeters, and this 10 centimeters do we want the answer? Is the answer from here, from where it left the spring, or from where it was pulled back? What we are about to calculate is this one. So we might need to subtract 10 centimeters from it if they wanted this one. I don't know which answer is right. I do know that based on the triangle here, L sine 30 has to equal 0.255. But 10 centimeters of that was when it was connected to the spring. So L is going to be 2 times 0.255, which is 0.51 meters. But it's 0.41 meters away from the spring. I don't know which answer they want. They're not clear. I could look it up. Would you like me to?
They wanted the whole thing. So I think it was 0.5.
This is what they accepted as the answer, was the 0.51.
My numbers were different. I think they did the whole thing. So they just subtracted.
That might have been it. On the AP exam, they're clear. They don't screw around. On the AP exam, they will give you a diagram and tell you which thing they are looking for you to find. They're not going to screw around. There's a part B to this, though. The ice cube was replaced by a 40-gram plastic cube whose coefficient of kinetic friction is 0.2. How far will the plastic cube travel up the slope? Does that change the problem dramatically? Not dramatically. It changes the problem. Now, herein lies the difficulty, and why I keep saying this. Does friction act over the smaller distance or over the whole distance? That's how I see it too. And we don't know what that whole distance is. We know the cube is 40 grams of plastic. So there's a couple ways we can approach it. We could do conservation of energy if you'd like. The problem with using conservation of energy is energy is not conserved. And although all the energy will be 1/2 kx squared again, how do you want to deal with this work done by friction when we have conservation of energy? The object will eventually make it to whatever mgh is going to be. So you have to choose. If we're doing this as before and after, you could say that take the amount of energy I have before and subtract the work done by friction. That would have to equal the energy you have after. This is another way of thinking about conservation of energy. That the energies aren't going to be equal because friction did work. You could also consider that before, the the energy was all elastic potential energy. Afterwards, the energy is all gravitational potential energy and heat that was left along the ramp due to the frictional force. These are alternatives to the way we did it. The way we did it in class would be work done on the spring plus work done by gravity plus work done by friction would have to equal the change in kinetic energy, which we know is 0. But all of these will be the same. They're all going to work out to be the same answer because work done by the spring is minus 1/2 kx squared. Work done by gravity is minus mgh. And work done by friction will be, I don't know, minus the work done by friction. That also equals 0. So we're going to get the same answer. So to do this, the real question is, how much work is done by friction? That's really what it comes down to. Everything else stays the same. The work done by friction will be the frictional force acting on the block, which is mu mg sine 30. And that has to act over the whole distance that it goes, which from our last problem is h divided by sine of 30. Right? Isn't that what L is? And that has to equal mgh. Now, once you get h, you still have to find that new length. But this is how it's done. They say the kinetic friction is 0.2, mass is 0.04. I don't think I have to go any further with this. Can I end it here? Yes, ma'am.
MG sine 30 or is MG cosine 30?
It's mg cosine 30. Sorry. I was getting a little bit excited and wanted to be done and got ahead of myself. That's 2 mistakes in 2 days.
Happens to the best of us.
Apparently, I'm just not the best of us anymore.
It's okay, this stuff is hard.
You're the best physics teacher we have.
You guys are screwed. Potential energy curve doesn't tell you necessarily what you might think it tells you. There's different ways for them to put this on the exam. So first, understand that it only describes the potential energy of the object. That doesn't necessarily mean that's the only thing graphed. Oftentimes on the exam, they will have perhaps a line on here someplace or tell you that maybe the object has a total of 6 joules of energy, but then presents you a potential energy graph. You have to understand that this only tells you the potential energy of the object, and often the systems are considered to be closed so that energy is conserved. If they provide you a line or indicate how much total energy the system has, they're indicating to you that this part of the graph is how much potential energy there is, and this part of the graph is how much kinetic energy there likely is. Now, this graph didn't do it this way, but that's not an uncommon thing to see on the exam. Moreover, if this line were to be here, it's also telling you that it's restricting where the object can be. I mean, if they tell you that this is how much energy the object has, and this is the potential energy curve that describes it, the object can only be then in places where its energy can be less than the total energy, which means the object could not exist in this region because it doesn't have enough energy to be there. But it could exist or be bounded in this region. This is known as a potential well, in that the object can only exist in these regions of space because these regions of space have the required amount of energy. Now, this problem isn't quite like this, but it's not far away from it. It doesn't have the line. Clearly, it has a way for you to determine what that line is. Get that out of the way, get that out of the way. So they say in the problem that what's the minimum speed of the particle needed to reach point B from point A? So at point A, the object has 2 joules of energy. To get to point B, it will need to get over this point here, which means it'll have to have enough speed to get past there, which means it'll have to have 5 joules of energy. Does that make sense to all of you? Understand where I'm going with this? Which means that it's going to have at point A 3 joules of kinetic energy to go along with its 2 joules of potential energy, so I can make it to the point here where it's going to have 5 joules of total energy in the form of potential. Then it can make it to B. You guys follow that argument? So to figure out the speed, you would say that the kinetic energy at A would have to equal 3 joules. So 1/2 mv squared equals 3 joules. 1/2 times 0.1 times v squared equals 3. You guys can do the rest. To find out how fast it's going at B, all the energy is converted now into kinetic. So how fast it would be going when its energy is 5 joules? 1/2 mv squared equals 5 joules. So this is part A of the problem. This is part B of the problem. All right. Any follow-up? So that suggests how we could deal with the energy for this problem. Again, no work was done by friction. So we'll have, get rid of the m's, and ultimately we're going to get V is going to be equal to the square root of 2g h minus, we'll say h naught. Is that good enough? So 25 minus 3. So you guys can figure out how fast we're going, but we'll need that later, I'm sure. Now, let's step away from that for just a minute and kind of figure out what we're going to do with that. The person is launched. I have vertical and horizontal here. They are launched at a vertical height of 3 meters, so their displacement will be minus 3 meters, making it to the ground for the projectile portion of this problem. The acceleration, minus 10 meters per second squared. I know for mastering, you got to use all 9.8. Enjoy. The initial y velocity is going to be whatever this is times the sine of 30 degrees, so half of it. And you need to figure out how long they're in the air. There's no shortcut with energy here. You're going to have to just do the whole thing. At the same time, the range, which is what you're looking for, is going to be equal to Vx, which is whatever that velocity is times the cosine of 30 degrees. And the time that's in the air comes from here. Yeah, there's no real shortcut from there. Go ahead.
Why did you do sine for 30 degrees times the
When they're launched here, like in any projectile, you have 2 components of the velocity. The vertical one is based on the sine function of the velocity, while the horizontal one is based on the cosine. I'll put V there, but I meant 30. You're welcome. Any follow-up? Look, there's just not a whole lot for energy here. On the other hand, you can use energy to help you figure out how high they go, because at that point, the gravitational potential energy will also become a max. But one of the more common questions on the AP exam is to ask about this height, assuming kids will forget that at that height, there's both kinetic and gravitational potential, because the object's moving sideways. So that is a very frequent mistake students make. So keep in mind that at maximum height here, the kinetic energy isn't 0. This has been on the AP exam, this question, with a few variances for conservation of energy. It's a great problem because it mixes enough content for it to be appropriate. Put a loop in there and you can get to force part 2. And I'm not saying this haphazardly. That's been on the exam twice. once a long time ago, once rather recently. Alrighty. You're launching an ice cube. Resetting the reference level really doesn't affect the answer all that much. But if the problem were reversed and you're allowing this to slide down the ramp, it does kind of affect the problem, because you have to decide at what point is the lowest point in the problem for how much energy the box has here or here. In the first example, it's going to be relative to the lowest point the box can get to, which is going to be where the box comes to rest against the spring. Where here, the box gets to the horizontal part of the slope. And because at this point its height isn't changing, all of that potential energy goes directly into the spring. You could ask, in which case would the spring be more compressed? The case on the left or the case on the right? And there's some validity in trying to figure out why there's a difference there. I would encourage you guys to think about that, or to think on this kind of question. And we talked about it a lot the other day, but I would encourage you to kind of think it through. Also, be aware of the point at which the object is traveling the fastest. Now, on this example, the object's velocity is at its maximum right when it contacts the spring. That will not be true in this example, because it will continue to accelerate because there's a component of the weight down the ramp. And it will continue to accelerate until the net force is 0 on it. All along here, the net force is 0 on the rock. That's why it's at its maximum speed. It's not true when the spring is placed on the ramp. None of that really affects this question tremendously. So in looking at this question, you asked specifically about part B. So I'm going to work on just part B of the question unless somebody needs terribly to see part A. Oh, good. Because part B and part A are very similar. They say that the ramp is 30 degrees. Let's go ahead with the assumption that the spring is on the ramp. We are told that there's a coefficient of kinetic friction along the ramp. Don't remember what it is, but it doesn't really matter. I'm not going to do the math part. The spring is pulled back some distance, I'll call X. And from there, the box is released, and the box travels from X to some point on the ramp where it comes to rest. Any question about that? All right. So here we go. You can do this problem from the standpoint of work, or you can do this from the standpoint of conservation of energy. If you're going to use conservation of energy, you need to kind of clarify what's happening with the energy. For example, when the box is pressed up against the spring, all of the energy, we'll call this before launch, all the energy is in the form of elastic potential energy. After the box is launched, the box slides up the ramp and attains some height above the reference level, which means the box acquires potential energy equivalent to mgh. However, we know that mgh is less than 1/2 kx squared. The gravitational potential energy will be less than the elastic potential energy because there is friction along the ramp. So you could consider that after the box was launched, there was some work done by friction to take away some of that energy, so that after launch, the total gravitational potential energy will have been made less by the work done by friction. Or, if you don't like that way of thinking about it, you can say before the launch, the energy was here, and after the launch, the energy was in the form of gravitational potential plus a now heated up ramp that was heated up due to the friction between the block and the ramp. Either one of these will have the intended effect of reducing the potential energy by the amount equivalent to the work done by friction. It's just different ways of thinking about it. Of course, you could also do work by the spring plus work by gravity plus work due to friction would have to equal delta K, which in this example is 0. The box started at rest and ended at rest. This will produce the same answers. They're all going to be the same. Now, to actually work this out, we need L. And we can write L in terms of H or vice versa. H has to be L sine 30 due to that triangle. So let's just do it this way. Is this all right? I would have 1/2 k x squared equals mgh, which is L sine 30. Any question about that? Okay. Plus work done by friction, mu mg cosine theta, that's the force of friction, all times L. And notice I'm making it explicitly positive because I'm saying this, I'm not talking about the actual work, I'm talking about how much energy was left on the track due to it sliding up the ramp. So I'm not going to put a cosine 180 here. I've already handled that by describing the energy here. All right? That's it. Solve for L. Okay, sir. And those are two clearly different distances. Now, I don't know what the problem specifically asked. I got the feeling from reading the question that they wanted the full distance traveled by the box, which would include the 10 centimeters of it being pushed by the spring, which is why RL includes that 10 centimeters in it. But friction was being done the whole time. So if you decide to make this your distance, then when you calculate the part with friction in it, you'll have to add the 10 centimeters to your distance. So that's why I think this is better. It also indicates that H is relative to the lowest point the object had at the beginning of the problem. I see two states of this problem. If I'm looking at it from the standpoint of conservation of energy, then I see two states. There's going to be the state at the beginning that looks like this. And in this state, my belief is the box on the table will be staying on the table, meaning its height will not change. Therefore, it will not experience a change in potential energy. So it has none. The box hanging off the table is not at its lowest point. I believe it will descend a distance h, suggesting that the box at the beginning of this problem has energy, mgh. I believe at the end of this problem, both boxes will be moving. Because at the end of this problem, the first box on the table will be pulled to the right and will have some velocity now, given to it by the fact that the box that's falling has been pulling on it. So my belief is that both boxes will have kinetic energy as the box off the table slides to the ground. So if this is the amount of energy before the system is released, I believe after the system is released, there will be kinetic energy between box 1 and with box 2. I believe they'll both have the same velocity just before that box hits the ground. However, I believe friction is going to take away some of that energy. So I think I should subtract the work done by friction. This is how I would set the problem up if I was looking at it from the standpoint of conservation of energy. I could put this on the other side, but I'd have to make it positive, indicating that that was energy that was left on the table in the form of heat due to friction. At the same time, I could say that there will be work done on M by gravity. I can say there'll be work done by capital M due to friction, and that's it. I believe this will, add up to provide a change in kinetic energy of the system. I could, if you would like, add two other forms of work here. The work done by tension on the big block and the work done by tension on the little block. If you would like, we could put both of those in there and we could add up all four forms of work and set that equal to the change in kinetic energy of the system. If we were to do this, the work done by gravity will be mg times h times the cosine of 0 degrees. Right? The force on that block is downwards. It goes downwards, and it goes downward a distance h. The work done by friction, well, I never addressed this earlier, so I'll address it now. It's going to be mu mg times h times cosine of 180 degrees. Any question about that? Now, for those of you who think this is going to be some kind of hard calculation, it's not. I don't need to know what the tension is. The tension on the big block is going to be in this direction, T, and the box is going to go in this direction, H. So the amount of work done will be T times H times the cosine of 0 degrees. The box that's hanging is going to experience a similar amount of tension, but the box is going to go downwards a distance h. So that'll be T times h times the cosine of 180 degrees. The work done by the internal force cancels out since it happens on both objects. When I add all this up, I will get I'm going to use a different color, mgh minus mu mgh equals 1/2 mv squared plus 1/2 mv squared minus 1/2 m0 squared minus 1/2 m0 squared. I mean, you guys see it's the exact same thing, right? We okay with that? Find V. Follow up? And I'm good with questions like this. No worries. These kinds of conservation of energy questions are great. I'd love to see. I hope you have these on the exam. It's good stuff. This is all over the multiple choice, by the way. Okay, they love to put this on the multiple choice and have kids think they have to solve for the forces, start looking for tension, get the acceleration, use a motion equation, when this is a one-step conservation of energy problem. If you have to do this by using forces, you're talking about 3 minutes maybe. But with energy, you can do it in one step. We're talking about 1.5 minutes. That's why it's a multiple choice question, to see if you know the most efficient way to solve a question like this. All righty. Moving right along. Next. In this problem, you would actually never do this because it would kill people. So we would never use springs to launch people ever. The impact of that spring on the car is generally with such high force that the people don't survive. It would probably break their necks. So no, you would not do this. But you could make a model. That would be fine. A model will work. Hot wheel cars? Sure. Little toy roller coasters at home? Fine. The Polly Pockets will probably survive the journey, as will your action figures. We're told that the initial hill is 13 meters above the level upon which it's launched, but that they then descend, I guess this would be 7 meters, so that the entire hill time below is like 20 meters. Is that right? So the spring will be pulled back a distance of 2.5 meters. And we're told that they're going to use a spring constant K, which is 13% greater than the effective spring constant that we will solve in this problem. So be aware, there's the spring constant we will get as our answer doing it this way, but they want a spring constant that is 13% larger for the answer. Now, what spring constant should we specify? We don't have to do anything that has to do with this 7 meters. All we got to do is get the car up to the top of this part of the hill, and it can have a velocity of 0. We'll just assume that it makes it just enough to get over. We know they're going to use a bigger spring constant. We know it'll actually go over the hill. All we got to do is get it to the top of the hill with a velocity of 0. That would be the minimum spring constant necessary. So at the top of that hill, all gravitational potential. Against the spring, all elastic potential. I don't need to worry about anything in between. We are making the assumption that there is no frictional force acting in between. Any question about this? All right, so I think that's all they want is a spring constant. So 1/2 k x squared equals mgh. We're solving this for k, with h being 13 meters. Now, we're going to use 2.5 meters here, 13 meters here. They want 9.8 there. When you get k, this is not the answer. You need a k that's 13% greater to get the right answer.